and you can put that in. Okay.
Board.
Yeah, we're only going to need it. So what are we up to? We're up to 15D, stationary points. So you'll notice there's a big fat amount of text and then like just a little bit of space to do some examples. So it really flows straight on from what we've been doing. What we're doing is we're finding stationary points, okay? So a stationary point is just a point on the function where the slope is horizontal, all right? So put really simply, the two most simple forms of a stationary point are the maximum and minimum points. Okay, so in order to answer these questions, you could just graph it and G solve the max and G solve the min, and that would be the solution. Okay, so that's the answer, but we're looking at using a calculus process to arrive at the answer. Okay, so one of the good things about this skill is you've got the answer that you know the direction you're heading. Okay, you can check your answer using your calculator. So there's stationary points, maximum and minimum. And then there is another type of stationary point, but we'll look at in the next question. Okay, so let's just have a look at where it says our process there. We've got in bold process. Part A, find f dash of x. So if this is f of x, let's go ahead and find f dash of x. That's going to be 3x squared, take 6x. And we want to draw the sign diagram of f dash of x. Okay, so that's all in step one. Find f dash of x and draw a sign diagram. So remember we've said if you want to draw a sign diagram, okay, you can just graph this and figure out when it's above and when it's below the x-axis. Okay, I'm going to perform the manual process here. For a sign diagram, we need the roots. That is, we need to know when it equals 0. All right, so we can factorize 3x, and then we apply the null factor law. X is 0 or x take 2 is 0. So there are our two solutions for the sign diagram. We've got 0 and 2. All right, and then I'm recognizing this is a quadratic. It has a positive a value, which means it's opening upwards, which means the shape that it's going to take on the graph is plus, minus, plus. Okay, and let's show you. It is 3x squared. Take 6x. Okay, so you can see from the graph, it is above the x-axis, and then it crosses at 0. It's below the x-axis, and then it crosses again at 2. Okay, that's this. We use the graph of f dash of x to tell us about the sign diagram of f dash of x. Now let's think about what the sign diagram of f dash of x tells us. Okay, so that's just the process of generating it. That's what we do in semester 1, right? We're figuring out how to draw a sign diagram. What's new to us is finding the derivative. So we're bringing those things together. What does this sign diagram tell us? But it tells us when we have positive slope and when we have negative slope. And let's think about that as well, okay? We've got positive slope until we get to 0. So it's increasing until it gets to 0, and then it has negative slope. So it's like, well, what is happening at 0? If it goes all the way up and then all the way down, we have a local max, okay? A maximum. So anytime the sign diagram of f dash of x goes from plus to minus, okay, from positive slope to negative slope, we have a local max, all right? And we can see that on the graph here, okay? There's the local max when x is 0. Similarly, we have negative slope until we get to 2, and then we have positive slope. All right, so if the sign diagram goes from negative to positive, we're going to have, it's going down and then up, we have what's called a local minimum. All right, and we can see that on the diagram as well. So we're going to go straight from here to talk about the stationary points on f of x. Okay, so we're going to say, therefore, f of x, that is the function, the original function we're talking about, has, and we can say local max. All right, we call it a local max because it's not the highest value of the function, it's just the highest value within the region that we're talking about, within the domain we're talking about. We have a local max when x is 0, and then we need the y value. Okay, how do we find the y value? We put this x value not into the derivative function, because that's going to tell us the slope at that point, into the original function. When x is 0, f of x is minus 2. So the y value is minus 2. All right? And we have a local min, all right, because it's got negative slope and then positive slope. It's going down and then up. At x is 2 and y is minus 6. All right, how do we get the minus 6? We take the 2 and we put it into the original function. Now what's really good about these questions, I've said, is we know the answer we're trying to find by this calculus process. And so in order to answer those y values, you can just get them straight from your graph. Okay, x is 2, y is minus 6 on the original function. All right, so what do? We find f dash of x and we draw its sign diagram. Okay, and we look, when does it change from positive to negative? That's a local max. When does it change from negative to positive? That's a local min. All right, let's look at the next one, which is f of x is x to the power of 3. Okay. Step 1 is to find f dash of x. Okay, that's going to be 3x squared. And then we're tasked with drawing the sign diagram of 3x squared. So when does this equal 0? All right, there's only one value that's going to make this statement equal to 0, and it is x being equal to 0. All right, so therefore x is 0. That's the root, and it's a double root because it's squared. Okay, the other thing to note is that a is positive again, so if we think of this as a quadratic because the leading variable is squared. It's positive 3, which means it's opening upwards, which means it has this shape, and it's touching at that point, so it's going plus and plus. Okay, so that's how I'm a maths teacher, I know these things, but how would we generate that sign diagram just using our calculator? Well, we would graph the function 3x squared, x squared, and we can see it touches at 0 and that it's above and above. Okay, so that's what I've done there. All right, touches at 0 and it's positive and positive. And this is the sign diagram of f dash of x. Okay, it's useful to label them. Now what we can see here is it's not a max or a min, isn't it? Because it's increasing, it goes horizontal, and then it keeps increasing again. All right, so that's not telling us about a local max or a local min. This is a new type of stationary point, and we call it a stationary point of inflection. Okay, so we learn more about points of inflection in year 12, but for now we do get to cover them and observe them. So let's look at the original function, which was x to the 3, and let's look at what that stationary point is. Okay, so have a look at the graph up here. If you're walking along the function, what are you doing? You're increasing, and then you go horizontal. All right, so you have a horizontal slope, and then you're increasing again. All right, so that's what a stationary point of inflection looks like. Okay, so we're increasing, we go horizontal, and then we're increasing again. All right, and then the other case, which is also listed in your booklet, you can see it there, is if you were decreasing, you went horizontal, and then you were decreasing again. And so the sign diagram that has a stationary point of inflection is going to be plus and then plus, or in this circumstance, which is listed in your book there, would be minus and minus about some root of the derivative function. So we have a stationary point of inflection when x is 0. We need the y value. When x is 0, y is 0 to the power of 3, which is also 0. Okay, these ones, okay, when you're asked to find stationary point of inflections, they're a little bit harder to, you can't just G-solve them. You can in year 12, we'll teach you skill how to do it, but for now, we don't know exactly how we can just G-solve the coordinates of those points. We can anticipate where it is, okay? You can see that it's increasing and then goes horizontal and then keeps increasing again. So you can roughly anticipate where it is, but it's the calculus process that generates the exact solution for the stationary point of inflection. Okay, so most of it starts like this, all right, pretty straightforward, increasing then decreasing. So we have a local max, decreasing then increasing, local min, and that's exercise 15D. Let's do it. Thank you, Brad. Sam present today?